So what we're here to talk to you today about is how graph technology is changing AI. That is the official title of this talk. What I wanted to call the talk was, it's not what you know, it's who you know. But the feedback I got was that no one would have any idea what the talk was about, so it's been relegated to this byline here. But it's not what you know, it's who you know. Right? We've all heard this term. What are we actually saying with this? It's the unpleasant reality that oftentimes the most predictive feature about whether or not someone is going to be successful in a given field are not their individual attributes, their IQ, their degree, even their work ethic. It's often who they know, their network. But what are we really saying when we say it's someone's network? Right? We're talking about things like, what community are they a part of? Who are the central or influential people and nodes within that community? What's the shortest path between this person to those influential nodes? How similar is their network to the network of other people who have been successful in this field? Now, what do these things have in common with each other? One of them is that they're incredibly difficult to fit into rows and columns. They're also incredibly difficult to fit into matrices. So what you end up with would be a predictive model that has some predictive capability, right? Where no one is saying that IQ, that degree, that some of these individual features aren't predictive, but you're leaving out an enormous part of what would actually help you answer this question, because you're trying to cram your predictive features into the wrong data model. What you need is a graph. You need a data structure that allows you to look at how people, places, and things are connected to each other and look at that complex network structure to allow you to bring in the features that will actually allow you to build a predictive model. So if we're thinking about taking this basic concept, it doesn't take an enormous amount of imagination to start looking at what are some of the use cases that we all in this room are working on where we're also not able to answer the question, who do they know? And we're stuck just looking at what they know. If we talk about financial crime detection, fraud, anti-money laundering, anomalies, being able to understand what community a specific account is a part of is incredibly powerful to understand whether or not they have any anomalous behavior. When we're talking about the interactions between drugs, genetics, and proteins, being able to understand those complex paths and infer relationships is really core to be able to do better drug discovery. With recommendations, with so many of the e-commerce platforms we go through now having millions of options, being able to look at more than just simple correlation relationships, but understand the complex paths that people take between products is really how the next step in accuracy and recommendation and engagement is going to be delivered. Customer segmentation, being able to look at not just clusters of people who have similar attributes, but how people are actually connected to each other and how people are actually making decisions around products and services to buy is incredibly powerful and helping to do better marketing. Within cybersecurity, looking at complex paths for intrusion networks. Within churn prediction, understanding who this person is connected to, what networks are they a part of, and have they maybe already churned from our service. Within predictive maintenance, being able to look at dependencies and understand cascading failures to do better root cause analysis. Or even in really how we all got started with graph, right? PageRank we throw around like it's a term that's existed forever, but the ability to look at how documents and knowledge connects to each other, understanding that as a graph is critical. But what are we even really talking about when we say a graph, right? Graph is a term that is used and abused in many different places. What we're not talking about is a chart, right? We're talking about the labeled property graph data model. So within the property graph, there are three core types of data structure that make it up. We've got nodes. These are generally objects. You can think of these as nouns, right? These are the things that we're looking at. You've got relationships. How are these things connected? Relationships have types, they have directions, they have attributes. But really what we're allowing you to do is look at relationships as a first-class citizen, the ability to query directly for relationships. And then we have properties of both those nodes and of those relationships. So you can get to those individual level attributes. You're not actually throwing those away. You're storing them in a way that allows you to look at that network structure and to understand how things are connected. So when we talk about a graph database or a graph technology, we're really talking about two major pieces to this. There's the data structure itself, how we're connecting these things. And in general, when we talk about that, we're going to talk about Cypher. It's the query language that Neo4j developed, is now open source, used by many vendors, and is a part of Spark 3.0. We believe will be an officially supported part of Spark. And then we're also talking about that underlying data structure itself. Right? Are you storing things natively as a graph, or are you mapping a graph from another input? And we'll talk about how you should think about those two things differently when you're exploring and building graph applications for yourself. So the whole point of the talk is how is graph technology changing AI? One of the things that I have found from the past several years of being a non-data scientist, working very closely with data scientists and in developing data science applications, is that you guys complain about how much data you have a lot. Right? The most common complaint that everyone hears in data science and that every data scientist is consistently making is we don't have the data. Right? We don't have enough data. Our data has poor quality. We don't have the right features in our data. What is the graph actually allowing data scientists to do? It's allowing you to make more accurate predictions with the data that you already have. What we're here to say is that you are throwing away the most predictive features that you have in your data by cramming them into a data format that just can't understand these relationships and understand this network structure. What we are not here to say is that all data science should be in a graph. What we're also not here to say is that you've been doing it wrong. What we're here to talk about is how can you start leveraging a graph alongside the infrastructure that you know and love, right, that you're currently using? How do you start adding those predictive relationship features to your current models? So just so everyone's clear, this is not going to be just a vendor talk, right? For one, a lot of what we're talking about is in Apache Spark, not in core Neo4j, but also we're talking about how graph adds value to AI across the field. So we're going to give you a lot of concrete examples of what people have done today, but it's also important to understand that the global research community is also waking up to the fact that graph is one of the most significant steps that data science is going to take over the next few years. So what you're seeing on the screen right now is an excerpt from ZDNet, kind of a summary from ZDNet of probably the most famous paper that has come out around graph AI in the past 6 months or so. This was Google DeepMind and MIT's paper. And I put up a couple major quotes to think through about why MIT, Google, and so many other leading research institutions think graph really is that next step. The first is the idea that graph networks are bigger than any one machine learning approach. Graphs bring an ability to generalize about structure that the individual neural networks don't have. That's going back to, it's not that you're choosing the wrong algorithm, it's that you're not giving the algorithm an understanding of network structure behind it. And the most important question for us as a graph technology provider, what DeepMind says is the most unanswered question for how to do this is not actually the math behind it, it's where do the graphs come from that graph networks operate over. What we're really going to talk to you about today are what are the approaches you should be taking, what are the algorithms, what are the models you should be building, but fundamentally it's how do you get your data into a graph shape and what should you be doing with it once you get it there. So when I said that I lead product management for Neo4j's graph analytics functionality, there are 3 core parts to that functionality. On the left is what we've been talking about most today. This is SparkGraph. So we have been partnering with Databricks for almost 2 years now to bring the property graph data model to Spark. As a part of Spark 3.0, the current plan with the Spark Project Improvement Plan is for a subset of Cypher 9, which is the current version of Cypher that we run, to move into being an officially supported part of Apache Spark 3.0. So what does that mean? It means that you will be able to use Cypher to create property graph mapping, so non-persistent snapshots of graphs on top of Spark. There will be an under-the-covers way in which, as you run these queries, you're able to create a graph that is mapped to your underlying data frame. So what does this allow you to do? It allows you to run the graph algorithms that are currently in graph frames and will later become part of SparkGraph in a way that understands that rich data model. It allows you to create graphs that you can then run queries against, and it allows you to stop writing so many damn table joins, right? No one I know has ever missed the idea of moving away from table joins. Cypher allows you to query relationships as a first-class citizen. what does it not allow you to do? It's not actually looking at the computational inefficiency under the hood, right? You're still fundamentally making those joins. So we're not fundamentally changing the performance. What we're fundamentally changing is the way for you to be able to understand and leverage that graph data model as part of your algorithms and part of your queries. At the same time as Spark 3.0 launches, we're also going to be launching Neo4j, or the official name is OpenCipher Morpheus, because it's a completely open source project, which is going to give you a new feature that currently, for anyone that knows Cypher, while you are querying a graph, we're actually returning results in a table, because the vast majority of applications that are built on top of our database have always needed tables as inputs. What we're going to be launching as part of Morpheus are graphs that return graphs. Right? You're able to take your sometimes incredibly large graph, return a subgraph, run more operations on that, return a smaller subgraph, and you're able to create an actual graph data pipeline. And one of the major reasons we're looking at doing this is many of the data sets that you guys work with are incredibly large. Bringing all of that data into a graph is sometimes both difficult and also not always necessary. Right, we're going to talk about some of the different reasons you want to bring data into a graph, but you often don't need all of your data to run a query, and you generally don't need all of your data to run a graph algorithm. Right? You generally don't need that in complete heterogeneous graph. What Morpheus is going to allow you to do is to create a graph pipeline so that you can run queries and algorithms against the right data, not all of your data. And another thing it'll allow you to do is to seamlessly bring that data into Neo4j's graph platform, where you do have a native graph structure. So you are focusing primarily, in addition to constructing the graph, on the performance both of queries in the database itself and of graph algorithms that are in our in-memory graph algorithm compute engine. So what that will allow you to do is create that graph pipeline within Spark, bring the right data into Neo4j, run efficient queries, efficient graph algorithms, push those features back to Spark so that you can bring them in to your machine learning model where it currently lives today. Right? We're talking about you don't need to change what you're doing, you need to add to what you're currently doing. And we'll talk about some specific examples to make that a bit more practical and real going forward. But so how should you be thinking about when we're talking about graph in Spark and when we're talking about graph in Neo4j? The way that I like to think about it is the functionality that we're working with Databricks on within Spark itself allow you to explore graphs in ways that you just haven't been able to do before, at scales you haven't been able to do before. It allows you to leverage that massive scalability of Spark, the incredibly powerful data pipelining, and the robust machine learning libraries that exist there. But it's important to note that what you're creating are non-persistent mappings of graphs, which means they're immutable graphs, right? You can save snapshots, you can come back to them, but when that graph changes, you're going to have to run through that pipeline again. And also they're non-native, right? So we're still going through the joins, and in algorithms, you're still chasing pointers often up to trillions of times across different tables, right? So this is a fantastic way to understand where you have graphs, and it's a fantastic way to start building graph features into your models. But once you realize that you have a real graph problem, right, you need to build a graph application, you need to build a graph model, you need to be in a native graph structure. That's where it's time to start bringing data into Neo4j and setting these two things up together. So this allows you to build persistent dynamic graphs. Dynamic meaning this is a database. You can change, increase, upload, delete nodes at will, and it's going to change with you. You're persisting all of that data in a native graph structure. You're going to have the increases in graph query performance. You're also going to have the increases in graph algorithm performance that come from looking at a native graph structure in memory. And finally, we are an exclusively graph company. The product engineering team I work with are consistently focused on new graph algorithms, new graph embeddings, new graph approaches. Once you realize that you might need to look beyond a small list of graph algorithms, there's going to be a constantly growing list of new graph approaches that sit on top of Neo4j. And to start trying to frame how you should think about leveraging graph technology as part of your current infrastructure, we broke out the steps of graph data science. So I want you to look at first the axes on this chart. On the left, we have complexity. What we're talking about is data science complexity here. What's the mathematical complexity with what we're trying to do from a data science perspective? On the bottom right, Delivery timeline, what this really is, inverse of how mature is this technology, right? So knowledge graphs are something that we and other vendors have been building for quite some time. I'll talk to you about how to get started in a knowledge graph. As we continue to move to the right, we're looking at slightly less mature enterprise technologies, right? So in DeepMind and many other papers talks around graph neural networks. It might not be the best place to get started if you're trying to build an enterprise application. But what we really want to talk to you about is how do you get started, what we have coming down the pipeline very soon to help you move up this list, and where do we think we're going as a graph industry. So what are each of these steps? The first we're going to talk about is the query-based knowledge graph. Fundamentally, the way you can think of this is you are building a knowledge graph to connect all of your different heterogeneous types of data and knowledge together so that a person can ask a question and actually get the results. Right? So there are so many use cases where you know what you're looking for, but you can't get it out of this gigantic this data lake that you have. We're going to talk about how you can build a knowledge graph to allow individual users to get the information they need to make decisions. We're then going to talk about query-based feature engineering. This is when you're moving away from having an individual person ask the question, you're moving towards building a model, but you're still having a domain expert know exactly what they're asking for, right? You're looking for specific patterns. Another way to think of this is you're running local queries, right? You're talking about individual nodes, individual patterns. I know what I'm looking for, but I need to return it across this large graph so that I can then take that and build it into my model, into my classifier or regression model. And we'll give you some examples around that. Where we're currently focused today is around graph algorithm feature engineering. This is when you want to take a step back from, I know what I'm looking for, I just can't get to it. And you want to let the network structure of the graph speak for itself. You want to start looking at global graph algorithms. So we have, and Spark as well, has a library of these global graph algorithms that are primarily unsupervised algorithms that allow you to look at network structure. So we separate them into community detection, centrality, shortest path, or path finding in general, link prediction, similarity, and graph embeddings. So Alicia will talk to you a bit about what are some of the ways to get started with that today. But in general, what data scientists are looking to do is run these unsupervised graph algorithms in order to generate those relationship features, pull them out of the graph, and then put them into a machine learning pipeline, which for everyone here is most likely going to be in Spark. From there, where we're headed in the next few months and where we're currently doing a decent amount of development is the idea of graph embeddings. This is where you are vectorizing a specific snapshot of the graph to then be fed into a model. Often this is where deep learning starts to intersect with the graph itself. In general, you're using something like gradient descent in order to determine what snapshot of the graph do you actually bring in. There are many different approaches to this. We are, as I said, now working with and moving towards an early adopter program for a few of different approaches towards graph embedding, so we'll talk to you about what some of those are. And where do we want to get? What is our goal here? What do we really want to be? We want to be the graph that graph neural networks operate over. So we'll talk to you a bit beyond just that Google paper about what is some of the work that is actually happening in industry now to get us to graph neural networks. So in each one of these, I'm going to try to give you a real-world example where you can track down code if you actually want it. And I'm going to try to give you an idea of how do I get started in Spark and how do I get started in Neo4j. So starting with a query-based knowledge graph. NASA is one of my favorite user stories around Neo4j, and it really shows actually the maturity of knowledge graph technology in general. So NASA has been around since 1958. They have been doing rocket science for more than 60 years. They, for much of that time, have been collecting all of the different information and knowledge they generate into their lessons learned database. It was probably one of the first gigantic and functionally useless data lakes that existed. An interesting case study in this is in 2012, David Meza, the chief knowledge architect of NASA, started looking at, we're now starting to look at engineering things that we haven't since the Apollo program. So in this case, the Orion capsule is going to be the first manned capsule we've built since the Apollo program. Fun fact, if you try to land a capsule upside down into the ocean, the astronauts are not going to enjoy that feeling. There's something called an uprighter, which is mechanical, so it hasn't actually changed that much in a long time. Just no one had built one since Apollo, so actually since the 60s, I think was the last time they looked at it. They knew they had that data. They knew they didn't throw it away. They had digitized all of their records. But what they also knew is even the best written query on that lessons learned database returned thousands of documents that were all different, functionally useless for someone who's trying to understand how have we done this in the past and what can I do now. So in 2012, David Meza started working with us at Neo4j. In 2015, so what you're seeing on the right is actual screenshots of the Neo4j browser at the time and some actual queries he had written. He combined topic modeling, some basic entity extraction with the Neo4j graph database to build the lessons learned knowledge graph. And an actual quote from him is that just on this Orion project, they were able to track down the right information, saving over 2 years of work and $1 million in taxpayer funds. I think the interesting thing about this is with the knowledge graphs, you'll get some of these large wins, but that's not really what you should be focused on. What you're focused on is the incredibly inefficient nature of people finding information, be it your customers, be it your employees, be it you yourself. What you're looking at is how do I connect something so that when I know what I'm looking for, I know I'm looking for an uprighter, I can actually find it, I can actually traverse the graph to get there. And the really important thing to think about this is this was done in 2012. Like, this is a data science talk. We live in dog years, right? Like, that was the same year that the Model S was launched. This is a very mature technology. We work with something like 76% of the Fortune 200. There are many other graph providers. If you believe that you have disconnected knowledge that you are storing in relational databases right now, this is a fantastic place to start looking at leveraging graph. From there, we're going to start talking about actual model building. So I'm going to hand it over to an actual data scientist to talk about data science.
Awesome, thank you so much. So once we have a knowledge graph, that's awesome. We can start querying things, we can answer questions, but you have to know what you're trying to get out. And what we're actually interested in here today is how do I make inferences from that knowledge graph? I want to take that data and I want to make predictions. So really, kind of the place that we envision people getting started in kind of a very simple, easy to understand use case, it's still really valuable, is what I would call query-based feature engineering. And what that means is you have a domain expert and they know something about that data in the knowledge graph, and they want to use that in a model. So when we talked about it's who you know, maybe you've got your tabular model with someone's IQ, where they went to school, what their work history is, and you say, but I know it's how far out they are from a successful person in my graph. So I want to write a query on that knowledge graph to pull back that metric. So a really nice real-life use case of this is what's called HetNet or HetioNet. You guys can check it out online at het.io. It's a knowledge graph used for drug discovery, specifically drug repurposing. So what this means is it's a knowledge graph that integrates over 50 years of biomedical data, so information from papers, patents, regulatory submissions, experiments, all in one place with entities like genes, diseases, chemicals, and various biological processes sort of interlinked with each other. And the goal is to use this knowledge graph to identify new uses for existing drugs. So the idea is there are drugs on the market approved for specific diseases that could work for other diseases, and we just don't know it yet. So the goal of HetNet is to predict those linkages between a drug that's on the market and a new disease it's not currently treating. And it's actually been used for this purpose. It's been around, I think, since 2015. It's fairly mature. So here's an example of a simple use case for HetNet. We have multiple sclerosis, which is a disease, and we want to know if the gene IRF1 is associated with it. And in the knowledge graph, you can think of this as a snapshot subgraph that's been pulled out. It's not directly linked. And we want to use domain expert-based features to predict if there should be a connection. So is IRF1 really relevant for multiple sclerosis? So what the folks behind HetNet have done is they've extracted what they call meta paths. So they have queries that say, given a gene and a disease, I want to predict the probability that they're actually associated with each other. And I'm going to look at the traversals across the graph, either between different genes or between tissues or biological processes, and see how many hops I have to go for that connection, and what do those traversals look like. And they ultimately come up with a score that's a weighting of how many traversals and how far they had to traverse across the graph to get to that linkage. And then that score can feed into a predictive model to say what is the likelihood that there's actually an association between this gene and this disease. And the idea is once you identify a new association, any drug that's associated with that gene now is associated with that new disease. So this is a really nice, clean example of how do you take all that data together, use a pretty simple rule-based heuristic to create a score, and then feed that score into a machine learning model. But we still have some limitations here, right? We're talking about this in the context of, I want to know if this gene is associated with this disease. And I have an assumption that the path lengths in between them across this graph are meaningful. I'm still not leveraging the full graph topology. So this is really where we see people getting started and is how you bring in domain expertise, but it's still a pretty supervised, manually tailored approach. And if you've listened to us talking for the last 20 minutes and you're like, this is cool, but I have no idea what you're talking about or how to get started or what you're actually meaning, for each of these sections where we're talking about a different use case, we're going to talk about how do I do this in real life. And when we're talking about knowledge graphs, the idea is you can use Spark to merge your distributed data into data frames and then reshape those data frames into graphs and start exploring with Cypher queries in Spark. Once you've kind of subset your graph, so you have your 10 terabytes of potentially relevant data, you've figured out what you actually want in your knowledge graph, you understand the queries you want to use, you can use Morpheus to build that graph data pipeline. So we have our giant graph, we're going to query it, return a subgraph, then we're going to move that graph into Neo4j, where we can start running those complicated queries using that optimized graph data structure, so they're much faster and more efficient, and then pull that information back into our machine learning pipeline to make predictions. So once we've done this, we want to kind of take the next step. And as Jake said earlier, where we're really focused right now is this graph feature engineering by graph algorithms. And this is really how we extract information about the topology and the connectivity of the graph with different algorithms or heuristics that are unsupervised. So instead of saying, I know this is important, I say, here are some algorithms that tell me about connectivity or importance or centrality. I want to run those, and then I want to bring those back into my machine learning pipeline. And so we've seen this figure before, and we really want to underline this message that we want to make use of your existing machine learning pipeline here. We're not saying set it all on fire, call Neo4j, and start again. We're saying you've got your tabular data in Spark. You have a machine learning pipeline that works well on rows and columns. What you can do is with graph algorithms in Neo4j, you can add more informative features that describe that topology, but bring it back into that matrix format that goes into your model building pipeline. So we're just adding new descriptive columns that ultimately may have more predictive power. So we have different categories of graph features. We can think about community detection really rises to the top. And what this means is you're detecting group clustering or partitioning in your graph. And so if you think about this in tabular data world, this is something like k-nearest neighbors or PCA, where you're splitting things out based on attributes. What we're using on community detection is what are the relationships, which groups interact more closely with each other. We also have metrics like centrality and importance, and that's things like the famous PageRank and connectivity. How connected is this node? How influential is it in the graph, et cetera. Pathfinding and search is sort of questions like, what's the shortest path between this node and this other node? Or what's the most efficient way to get across the graph? And so when you're looking at things like, what's the shortest path between me and someone influential, you might use a pathfinding algorithm. Heuristic link prediction is just looking at, given two nodes and what they're connected to, how likely are they to be connected to each other? And you can kind of think of that as an extension of the HetNet example we looked at. Similarity is sort of how similar are two nodes given what they're connected to. And you can think of it like set overlap calculations. And then finally, embeddings, which we're going to talk about a little later, are basically vectors or bit strings that capture your network topology in something that's machine readable. So a really nice example of how do you take your existing model building framework and make it better with graphs is financial crimes. So most major financial institutions have existing pipelines to identify fraud. And fraud could be anything from money laundering to first-party fraud with fake users, or it could be third-party fraud with people stealing identities. There are existing ways of finding fraud, right? It might be a rule like, if I see this many transactions in this time window, red flag. Or if I see a transaction happening outside the area where this person lives, maybe a bad thing. What we're doing right now as part of our early adopters program is working with companies to bring graph-based features that improve accuracy. So you can think of your kind of transaction data as a network, right? You have account holders, you have identifiers about them, where they live, what's their social security number, what's the IP address they log in from, who do they transact with, and that's a network. And so you can use those graph algorithms to extract information about how those accounts are interacting with each other. So some examples of what we're looking at using right now is things like connected components, which identifies disjoint subgraphs in your graph. So if you run connected components on an account graph and you find these accounts are a distinct subgraph where they're all sharing the same address and social security number, that's probably they're involved in some kind of first-party fraud. You can use PageRank looking at, say, volumes of transactions between users to measure how influential a node is. And that could tell you about unusual transaction volumes, too much money flowing between accounts, or something like money laundering. Louvain is another good approach. This is one of those community detection algorithms that finds out who interacts with who frequently. So if we think about this accounts graph, the accounts that interact with each other very frequently have a lot of transactions. You run Louvain and you'll be able to pull those out in an unsupervised manner and perhaps uncover money laundering rings. If you have labeled accounts, I know this account is fraudulent, you can seed those communities and find the communities that already have a fraudster in them and use that to follow up. You can also use something like Jacquard similarity to measure how similar are two accounts based on who they're interacting with. So I know this is a fraudulent account. I have this other account. I can use this similarity algorithm and say, this account actually behaves a lot like this fraudulent account, and add all of these as columns into my tabular data for my predictive model. And in case you're like, maybe she just made this up, I did not. There is a ton of research in this space. This is a snap of a table from a 2014 review paper that just listed all of the algorithms that were available. And so this is 5 years ago, and it's too small to read, but I hope you can see there's lots of rows and lots of columns. There's a ton of algorithms looking at all different flavors of how do you combine these. And if you do a patent search for graph-based fraud detection in the last 10 years, there are over 48,000 patents. So this is a growing area of interest and a really nice way of thinking about how do I start taking topology and putting it into my graph or into my model. Circling back to how do we get started, again, you can think about this SparkGraph ecosystem of pulling my data together into a graph shape, using Morpheus to query it and generate the relevant subgraphs, and then moving into Neo4j and running those native graph algorithms to extract your features. And what's kind of cool here is when you're in SparkGraph, there are some algorithms you can run to kind of experiment with and get a sense of, hey, PageRank looks informative, connected components, I see multiple subgraphs, and you can use that to inform when you move into Neo4j, I actually want to run more centrality calculations. And once you've run your algorithms in this persistent graph, you can write them back and store those predictions, or you can pipe them back into your machine learning pipeline in Spark. And just to give you an overview, I said, oh, we have all these algorithms. This is kind of a quick list of the graph features or the graph algorithms available in Neo4j as of 2 weeks ago. You can see we have a lot of different flavors of each category. Each one tells you something slightly different. When we talk about experimenting in Spark with their graph algorithms, you can see that the ones in bold are the ones that are available there. And the reason that there's sort of different subsets is in Neo4j, we're running our algorithms on an in-memory graph. So they're efficient, and you're running on a single unified graph instead of chasing across distributed data. So that lets us implement more algorithms sort of more efficiently. So moving on, so that was really where we're at today. I spend a lot of my time talking to early adopting customers and people who are interested in, I have a machine learning pipeline, I want to put graph-based features in it. Where are we heading next? So what's really exciting for me is the concept of graph embeddings. And they're nice because they sit in between graph feature engineering and graph native learning. So you can use an embedding, just a bit string, as a feature in your machine learning model. You can compare two embeddings to each other to look at similarity, or these are often the inputs into a deep learning model. So when I talk about embeddings, I'm talking about taking your graph and transforming it into a vector or series of vectors that describes some aspect that you're interested in, that you've trained in a supervised way. It can represent topology, connectivity, or attributes. And there's kind of three general categories: vertex or node embeddings that sort of describe, given a node, what's the connectivity around this node. Path embeddings that describe traversals across the graph, as well as graph embeddings, where you're trying to encode an entire graph into a single vector. And that's sort of relevant in the chemistry space, or where a single graph has an attribute itself. And so this image at the bottom is from a deep walk paper, and it's sort of looking at how do you actually translate a graph into an embedding. So for deep walk, you take individual nodes, you take random walks across the graph from those nodes, and then you can train a skipgram model and use gradient descent to optimize your vectors that describe what those nodes are in the graph. A really nice example of how do you use graph embeddings. So it's like, cool, we can make some bit strings, this is interesting. How do I use these in real life? One thing that I'm really excited about is graph embeddings for recommendations. So eBay recently published a paper called Explainable Reasoning over Knowledge Graphs for Recommendation. And conceptually what this is often when we talk about recommendations on knowledge graphs, what we mean is collaborative filtering. So I listened to this song. What songs did my friends listen to? What songs have my friends listened to that I haven't listened to yet? Maybe I would like them. I listened to a song in this genre. What other songs in this genre have I not listened to? These are all based on rules. What you can do with an embedding is identify those paths across the graph between me and things that I like, and then use that to train a model that can predict novel things I might like. So here we have a user likes a song, and that song is part of a knowledge graph, where the song is sung by someone, it's part of a genre, it's interacting with another person, and ultimately you want to traverse that graph to come up with a new prediction. And so what they talk about in their paper is they're training an embedding layer based on path traversals between users and songs in the graph. They extract all of the paths up to 6 hops, and they look at not just the nodes in the graph, but also the edges. So Alice, Shape of You, and Ed Sheeran are nodes. Edges are interacted, sung by, produced. Those are trained. You extract an embedding that describes all of those traversals, and then you feed that into an LSTM to ultimately come up with a prediction. And what's exciting about this is those path traversal embeddings give you a probability. So you have all these possible traversals. You can come up with the probability that I like a new song based on these traversals that are present in the graph. And you can think about using this to move away from the boogeyman of deep learning, if it's a black box. I don't know what this came from or what it's telling me. You're just telling me the deep learning model came up with something. With this, you have path traversals that you can use to say, I think this is a reasonable recommendation because this is the path that was followed in the graph. So if this is exciting to you and you're ready to get started, this is sort of where we're heading in the next couple quarters. So right now, our labs team has implemented DeepWalk and DeepGL as prototypes. They don't scale well, but they're proof of concept of can we do it. We're actively working with EAP partners as well as internal resources to develop more and more relevant embeddings. If this is something that you're like, I am super excited about this, I want to do this tomorrow, please come talk to us afterwards. What we're really working on is what embeddings are the most relevant for the use cases that people want to work on. Now I'm going to sort of shift gears into this is where we're heading in the future. So graph native learning on graph neural networks. This is just deep learning, right? So we're talking about training multi-layer neural networks using gradient descent, where you have input layers, some sort of transformations that happen, and a prediction on the end. Graph native learning is when you have a deep learning model that takes a graph as an input, performs computations like edge and node updates, and then returns a graph in the end. And the first time I read the DeepNet paper, I really struggled to wrap my head around it. I was like, what does this mean and why do I care about it? So a really nice example of where graph native learning is actively being used is in the chemistry space. And this is a paper from Bradshaw et al. This year, where they looked at electron path prediction, where you can represent individual molecules as graphs. If you have two molecules in a reagent and you combine them, what are they going to produce? Both what compound will they produce, and how will they produce it based on electrons moving around? And so here's just a quick heuristic an example of what this prediction looks like, where you have individual atoms in your molecules, you update the edge connectivity, and then ultimately update the properties of those molecules and arrive at a new compound. So this is a really nice example of how do I take this abstract idea of I have a graph and I want to predict a new graph. What does this mean? Chemicals are graphs. I have two chemicals. I predict a new chemical. So I'm now going to hand this back to Jake.
And I think we are officially out of time, so I will jump to what are the resources, now that you understand the steps of graph data science that you should be taking, what are the resources to get you started? We actually just published our Riley Graph Algorithms book by Mark Needham and Amy Hodler. Amy is back in that left corner if you want to talk to a superstar graph algorithm author. You can download the Neo4j Graph Algorithms library. I should point out that you can also download graph frames and start working with SparkGraph algorithms. You can check out all of our documentation on all of those algorithms to understand how to call them, where you should be using them. And also you can reach out to us directly. As Alicia said, we're currently working with enterprise early adopter customers. If any of this seems like it would solve a specific problem that you're working on today, please come talk to us after the talk. Questions?
Thank you.
Yes.